So we will now switch to Armand Jordana, who recently joined the Gepetto group. So I think you have to just wait that they switch the slides.
Oh. Little spoiler, sorry.
And Armand, the floor is yours.
Okay. Hi, everyone. Thank you for having me today. So I'm a postdoc in the Gepetto team here at LAAS in CNRS. And so the title of my talk is Handling Contact and Constraints in MPC for Legged Robots. So Shize has talked about VLAs that combine vision, language, and action. And so today, in my work, I will mostly present the action part. So I will show how we can generate motions. So in the past years, we have seen a lot of progress in robotics with our famous videos of the animal robot in ETH opening a door, at LAAS performing parkour. I think we can safely say that we are able to achieve optimal behaviors on a robot. And yet, this is mostly confined to predefined settings, such as factories or labs, as you can see in those videos. And I think one of the reasons why we're not seeing this outside in the real world doing useful thing yet is that we are not able to achieve safe and cautious behaviors. So if you look, for instance, at the videos of those cats here, clearly there is some notion of risk. Obviously, here the risk is falling. Both of those cats are able to adapt in a very natural way. So here there is uncertainty and the risk, and given this information, they are able to slow down. And when you think about it, generating algorithms that can automatically adapt the speed or just the motion according to the uncertainty and the risk is really a complicated problem. And that's what I studied during my PhD. And today I will show like a few ways in which we can make progress in that direction. So first, let's take a look at which controller is running under the hood of those nice videos that I showed you. So we have both of those videos are running with MPC, which stands for Model Predictive Control. So the idea of MPC is quite simple. We are going to constantly replan in real time over a predictive horizon. So if you think of this little toy robot that wants to go from its initial state to the goal, well, what it's going to do is very simple. It's going to think or like plan one path from the initial state to the goal. And if something goes wrong, let's say it starts going through that path and the disturbance hits the robot, it's going to be pushed away to a new state. And MPC automatically replans a new trajectory to reach that goal. And so what's very nice is that this path, this new path, is not necessarily the same one as the previous one. It's very versatile. You can find the new optimal thing in some sense. And so this is what makes MPC that versatile and effective in practice. However, there's a drawback. Planning online is very computationally expensive, and so in practice, we have to do a lot of simplifications. Usually, we are going to ignore safety to save compute time, and we are going to ignore any notion of safety and uncertainty. So this can lead to catastrophic results. For instance, this is a famous one of LAAS where it tries to do some fancy motion and misses a step. So here, clearly, there was some uncertainty in the perception loop, and it was completely ignored by the controller, and this led to this catastrophic result. So the question is, how can we go further? How can we bridge this gap and ensure safety while reasoning about the notion of risk? So here's my outline. So first, I will talk about safe nonlinear MPC. Then I will talk about how we can deal with the infinite horizon. Here I will show like a few connections with reinforcement learning. And lastly, I will talk about how we can handle contacts, and I will talk a bit more about zero-order optimization. Okay, so I said that this toy robot had to plan a path to reach that goal. So what I meant actually is that we're going to solve an optimal control problem. So this is how you formalize it. You have a state X, which is, in our case, the joint position of all the robot, and the velocity of each joint. And so then we have a control input, which is typically the torque that we apply in each of our joints. So the goal here is to minimize our cost function that's defined over a predictive horizon. So here L is the cost function, and capital T is the time horizon. So that's how far the robot can see into the future. And this minimization of our cost is done subject to two constraints. The first one stating that we should start from where we are at the initial time, and the second one stating that we should satisfy the dynamics of the robot, which is nothing but the second law of Newton. And so this problem is very challenging to solve because in practice, we only have 1 or 2 milliseconds to make a decision. And if we don't have an answer in a few milliseconds, then the robot falls. So it's quite difficult, especially that this problem is completely non-convex. It's highly dimensional. And so in practice, practitioners in robotics have come up with very tailored algorithms such as DDP or FDDP, which is a variation of DDP. DDP stands for differential dynamic programming. And so this has been quite effective in the recent years. And one question I asked myself during my PhD is why not use standard optimization techniques? Because in the end, this is nothing but an optimization problem. So maybe we could use Newton method, or here, because we have constraints, some sequential quadratic programming, some really textbook techniques. And the first answer I found in the literature is that if you do dedicated algorithms, you will have a linear complexity with respect to the time horizon, while with standard optimization algorithms, you can have up to a cubic complexity with respect to the time horizon. And this is really something we cannot afford when we want to find a solution in a few milliseconds. However, this is not entirely true. It's actually possible to find solutions with a linear complexity. And what I will argue today is that this has been slightly overlooked by the robotics community. It was actually well known in the control community for a very long time, but I think roboticists have slightly missed this, and I will show you how by just following standard optimization techniques we can have state-of-the-art results in robotics. Okay, so let's dive in with VSQP, but we could take any other textbook technique. So VSQP is really a standard optimization technique to handle constraint problems. The procedure is quite simple. We are going to iteratively quadratize the cost, linearize our constraints. So here, it's going to be the dynamics. Then we are going to solve an associated quadratic program and use the solution of this QP to take a step according to a line search procedure, for instance. And so here, the challenge for us is really to solve the QP. It has a huge dimension, and this is really the compute bottleneck. So fortunately, we are very lucky in robotics. We have only optimal control problems to solve, and they all have a very nice structure. If we look at the KKT conditions of our QP, there are a lot of zeros. It's actually a tridiagonal system that we want to solve. And so, well, this is very simple to solve efficiently. We can just do some recursions with a Gaussian elimination, and this gives us a nice linear complexity. And actually, if you write down the equations, you can recover recursive recursions, and this is how you can connect SQPs to all the other algorithms such as DDP. And so in the end, we can implement standard optimization algorithms with really the same equations as DDP-like techniques. And so, again, this was known in the control community, but not really applied in robotics. So what we did was to benchmark and see what worked best. So here you can see a nice motion with a humanoid robot. And we compare DDP and its variations against SQP. So here, the higher, the better. So you can see that the SQP in blue solves a much more problem much faster. So I think we can see that in 50 iterations, it can solve 80% of the problems, while the other techniques take much more time. And really, the implementation of each algorithm is really using the same recursions. It's only, on one hand, we are using SQP, which is a textbook algorithm, and on the other hand, we are using a more tailored technique that here doesn't work as well. So with this insight, we decided to go further and add constraints. And so here, what's really interesting is that here, because people were coming from the DDP perspective, without optimization techniques, they were not able to handle the constraint case because it was much more complex. However, when you come with optimization principles, adding constraints is very straightforward. You can just apply the same recipe, have an SQP, except that now you are going to have an inequality quadratic program to solve. And so there is nothing new, except that the QP has inequalities, but this is something that we know how to do. You can, for instance, use OSQP or any other state-of-the-art QP solver. And what we did in our recent work was to find a way to exploit the sparsity inside the OSQP. So if we look at the equations, we have the same sparsity pattern, so we can leverage it to get linear recursions and get an implementation of OSQP that's linear with respect to the time horizon. And so what I will show later is that this can give us really nice results experimentally. So here's a small comparison where we compare the vanilla OSQP in red against our tailored implementation. So as expected, as the horizon or the state dimension here grows, we get a huge speed up, which is completely expected. If we know the sparsity in advance, we're going to do much better than the default sparse linear algebra of OSQP here. All right, so we have released an open source implementation, and since we have used this work in many other projects, I will show you just a few examples. So here, it's a KUKA robot with 7 degrees of freedom performing ascending task. So here it's basically drawing a circle while applying 50 Newton on the table. So here those are various techniques. Here the point that we wanted to illustrate in this paper was that MPC typically struggles in a force control task. So here what you will see is my colleague pushing the robot during the motion. And so the first plot shows the force, and pay attention at the force tracking. You can see that it should be at 50 Newton, but each time my colleague pushes the robot, well, it deviates a lot from the static reference. And so this is a well-known problem from MPC. It's basically due to the fact that we don't integrate the force in the state. And so here we propose a very simple way to circumvent this problem by doing some online estimation, so nothing different than Kalman filtering. And as you can see, now each time my colleague pushes the robot, we're able to match the 50 Newton reference in force. Okay, so that's one example of application. Here's a second example of application that was performed here at LAAS. So this is a Panda robot that has to avoid this spherical obstacle. So here it's a very highly dimensional problem because we are defining the obstacle avoidance as a set of constraints between each part of a robot and the sphere. So we have as many constraints as we have parts of the obstacle. And we are solving this within 1 or 2 milliseconds. Okay, so then we can always do more to please reviewers and combine everything. So here's an example. So yeah, those were like the first demonstration of MPC with hard constraints solved at this kind of frequency on a torque robot. And you can see that it works well. So you have a hard constraint that states that the robot should not collide with the robot. And then the soft constraint, so the cost function that says that we should follow the circle. So of course, if you put the obstacle in the way, it cannot achieve the task. Okay, so now I want to show you like a small limitation, actually an important limitation. So here, this is a pick and place task. So it's a simple task where we want the end effector of a robot to go from the one green dot to the other green dot. And as you can see, we placed a rod, so a black rod in the middle. And now the robot is not able to go from one point to the other. We are stuck in a local minima. So this can be due to multiple reasons. It's a common problem of gradient-based techniques. And so I will present you like a few ways that can help us mitigate this problem. So first, let's take a look at this little toy example. So we have a point that wants to reach the goal, and we have this weirdly shaped obstacle in the middle. What's really interesting here is that if you take the optimal control problem formulation here on the left, the same one as I showed you before, if you take a short horizon, the optimal solution is to go straight into the local minima. Basically, it's not able to foresee that there's a way to get a lower cost by taking a sidewalk, like the green one is doing with a long horizon here, it's equal to 200. So if we have a very long horizon, it's worth it to not go straight to the goal, to avoid the obstacle, and then achieve a zero cost at the end. So ideally, what we would like to have is to have this infinite horizon value function. So this is something that has very well been studied in the theory of MPC in the 90s mostly. And what you can show is that if you follow this thing, you can have global stability, meaning that no matter where you start, you will reach your solution. However, all this theory is for linear systems, and in practice, our functions are nonlinear. So we need to rely on some form of approximation or learning, and this is what we did in this project, where we approximated this infinite horizon formulation with a value function learning approach. So here what we do is very straightforward. We have this infinite sum, and we decide to split it into two terms. The first term is the model-based term, so it's the finite sum, and the second term is a neural network that approximates the infinite horizon behavior. And so this is really classical concepts from reinforcement learning, except that now we have constraints. So we can still use reinforcement learning techniques such as minimizing the Bellman error to do the training, but now because we have constraints, we need to apply hard constraint when we do the minimization when we have a Bellman error. But so this is now something we can do with the solver I introduced earlier. And once we have trained this value function V, we can deploy it and see that now we are able to get more global behaviors. So here the only difference is really that the terminal cost is this learned value function. It's only a one-line difference in the code. And now you can see that it's able to avoid nicely the obstacle. So the same thing can be done by moving the goal around. We can also move the obstacle. It's very generic. And one thing that I think, so here we can move the obstacle. So one thing that I want to insist on is that this, in my opinion, is a very principled way to have safety when we have a learning module on a very real robot. Here, for instance, I show you a configuration of a rod that has never been seen during training. And so you can see that nothing explodes. The value function is surely giving random numbers because it has never been trained on this configuration. And yet, the safety is guaranteed because, so we are not colliding with the rod because the constraints are applied at each time step. And so, as you can see, it's maybe not optimal. It's not going to find a way around the obstacle, which makes sense because it has never seen this during training, but at least it's safe. So I think that's a very interesting way to combine learning with model-based techniques in order to have safety during deployment. So this is another example where I push the robot against the table. It has never seen such perturbations during the learning, but because I have a constraint stating that I should not be too close from the table, it's able to resist, basically. Okay, so this concludes this second part of the talk. Now I want to talk about contact. So in my first videos of this talk, I showed you humanoid robots, quadrupeds, that are constantly doing contact switches with the ground or with the objects they manipulate. And gradient-based techniques are usually not very good choice for this kind of problems. One of the reasons for this is that if you look at the optimization landscape of your problem when you have contacts, it's usually going to look like something like this. So we have non-smooth objective functions, we have multiple local minima, and I think the worst is that we have zero gradient regions. So like no gradient techniques such as SQP can really work. So one idea that is getting more and more popular these days in robotics is to use zero order or derivative-free approaches. So here are a few examples. We have CEM that is quite popular, CMAES, and recently MPPI, which I think is only very well known in the robotics community, is gaining a lot of traction. So I want to explain a bit more of this because I think maybe there's some nice things that are hiding behind this algorithm, who is now more and more used in practice on robots. So let's take a very simple way to solve this nasty non-smooth problem. One approach is to do randomized smoothing. So this is the formula here you can see on the left. This is something that has been very well studied by Nesterov and many other mathematicians. The idea is to do some local averaging of your function in order to have a smooth function. And then you can do gradient descent and apply all the principles that we have seen earlier. However, this example is quite, it's a weird example because we have two minima, one global and one local one. And what you can see is that the randomized smoothing curve here, the orange one, gives kind of a same weight to both minima. The reason here is that the global minima is very narrow and the bad local minima is very wide. So obviously randomized smoothing gets strict, and ideally what we would like will be something like this. So this is the log sum smoothing or Laplace transform. You don't really need to look at the formula, to be honest. It's really the intuition that it's going to give more emphasis on the solutions that have a deeper minima. And of course, this smoothing has a much higher variance. However, with modern compute, with GPUs, we are able to fight this higher variance with more and more parallelized samples. And what we recently discovered is that this smoothing is actually the one that is behind the MPPI algorithm that is now more and more used in robotics. So I think this is an interesting thing to see, because now that we understand that MPPI can be seen as an optimization algorithm, which was not the case before, we can add acceleration concepts, we can do all sorts of things, maybe even add constraints. Here it's an example where we add acceleration, and so you can see, so it's a balancing task, so it has to stay in place on one foot, and so you can see that the MPPI controller really doesn't work really well, and if we add acceleration, we are getting much more precise solution, and we are balancing much more accurately. So the key takeaway is that we can understand MPPI as from an optimization perspective, and that we can accelerate it with optimization principles. And so a last question I asked myself recently is, okay, why not use this understanding to derive novel reinforcement learning algorithms? And so this is what we did. So here, the idea was very simple. It was to estimate the gradient in DDPG with randomized smoothing or this MPPI smoothing that we saw. So we tested this idea. So it's just a one-line change. When we differentiate our learned Q function in DDPG, we are going to do a randomized smoothing instead. And so what we can see here is that we are going to have slightly better results. So here, the higher the better. You can see the baseline DDPG in blue and our variations in orange and green. And you can see that we have a better performance. And we did this with also more modern versions of DDPG and get similar results. Okay, so this concludes this part of the talk, and I want to briefly mention some ongoing work that we are doing here at LAAS, and that relies on MPPI. So this is work led by Constant Roux and Olivier Stas. So you can see Constant performing a squat motion, and then what we are doing is that we are using MPPI to retarget this motion into the robotics configuration space, and then H1 performs the motion. So this is, I think, the first or second trial, so you can see that the robot is performing a bit weird, but it's only a matter of tuning before the motion looks nice. And okay, so to conclude what's missing, I think for sure, if we want to have more safety, we need to have more complex perception still. And I think zero-order optimization techniques are very promising to solve those problems with a lot of contact switches. However, it's really not clear how to add safety, and so that's something that I still want to investigate. And with this, I want to thank you all for your attention.
We have time for questions.
For the infinite control. So when you hybridize it with reinforcement learning, I was wondering how you make the result of the SQP problem differentiable in the loss, or do you model the minimum, the result of the SQP problem as a reward signal, or could you say a bit more about it?
Yes. So the way it happens is that the SQP optimizes this optimal control problem formulation, where as a terminal cost, we have our value function. So there is a little challenge, as you say, because our terminal cost is going to be a neural network. So for this to be differentiable, we take a nice and smooth activation functions. And a nice trick that works well is to predict is to write the terminal cost, the value function as a sum of least squares of a neural network. And so this adds nice property in practice.
Thank you very much, Armand.